Welcome to Algebra, Solving Systems of Equations, Part 1. In the last unit, you learned all about linear equations, functions, lines, their slope, how to graph them, and how to write equations for them using both slope-intercept form and standard form. Now we begin the study of two lines at a time, called a system of equations. Let's dive in and see what this is all about. A system in algebra is when there are two or more linear equations being considered at the same time. In this unit, we will learn about how to solve systems of equations. Below is an example of a system of two equations graphed in Desmos. First of all, notice the version of Desmos being used at the URL listed below. This is the special version used in testing on the Texas STAR test for 8th grade math and algebra. We'll use this version from here on out. Next, see that the two equations only show the right side of the slope-intercept form, mx plus b. This is okay and will work in Desmos. We will use this abbreviated form from time to time when graphing. Finally, notice these two lines cross at the point -4, 2. This is the solution to this system of equations, the one point both lines have in common. This means that mathematically, if you substitute -4 for x in both equations, you will get the point y value of 2. This is what it means to find the solution to the system, finding the point where the two lines cross, the point that is common to both lines, the point whose x and y values work for both equations. As we just saw on the previous slide, when two equations are being considered, the point that works mathematically for both equations is considered the solution to the system. We saw this by graphing the two equations and observing the point where the lines crossed. Let's demonstrate in more detail. Here we find the solution by graphing. Two equations are given, y equals 3x plus 2 and y equals -2x minus 8. Both in slope-intercept form, very easy to graph, and in doing so, we find the point where the two lines cross, which is the solution to this system of equations, -2, -4. To prove the solution works for both equations, we substitute the x value in each with -2. Work it through to find the y value, which matches the solution using both equations. When both equations are in slope-intercept form, another way to solve the system is to use the algebraic process, setting both right sides equal to each other since they are both equal to y. This is another way of solving the system, which yields the same result as graphing the two lines and observing the intersecting point. Solving for x gives us the value -2. Substituting -2 in place of x for either equation results in the value -4 for y, matching the solution we found by graphing, the point -2, -4. Here is another example. Both equations in slope-intercept form, easy to graph to find the solution, which is the point 2, -1. To prove this solution works for both equations, we substitute the x value in each with 2. Work it through to find the y value, which matches the solution. Because both equations are in slope-intercept form, both start with y equals, both right sides can be set equal to each other, and we solve algebraically, resulting in the same solution as we found by graphing. Here is another system of two equations, but something is different. Can you spot it? Pause the video if you need to. If you noticed the first equation is not in slope-intercept form, you are correct. To fix this, convert it to slope-intercept form using the process you know. And now it is good to go either by graphing both to find the intersection point, or by setting both right sides equal to each other and solving for x, and then substituting x into either equation to solve for y. Let's look at another example. Two equations in slope-intercept form. Solve algebraically by setting both right sides equal to each other, solving for x, and then substituting x into either equation to find y. The graph of this system of equations shows the same result, the point 2, 25, as the intersection of the two lines, the solution to the system. In an earlier lesson on solving complex equations with variables on both sides, such as the one shown here, we used the algebraic process to solve for the variable, using the distributive property, combining like terms, combine the variable terms on one side, move the constant values to the other side, and finally isolating the variable by dividing by the coefficient to find the solution for x, -2 in this case. Now we can use Desmos to check the answer, entering each side of the original equation and observing the x value of the intersecting point to verify our algebra was correct. The value of y in this situation is not important. Here's another equation with variables on both sides, solved algebraically by isolating the variable on one side, constants on the other, divide by the coefficient, and finding the final value of x, -6. Graphing both sides of the equation in Desmos shows the x value of -6, again verifying the correct solution to the equation. Again, the value of y is not significant. Here is a sample test question assessing this concept of solving systems of equations. A graph of a system of equations is shown on the grid, and then 4 pairs of equations are shown as choices. You are to find the choice that is best represented by the graph. Take a moment, pause the video if you need to, and work out what you think is the best choice. Since all the choices are in slope-intercept form, the first step is to find the y-intercepts of -3 and -8 in the equations, as you can see on the graph. Well, it seems all the choices show these two values, and so the next step is to determine the slope that belongs to each one. For the line crossing at -3, the slope is going upwards, and so the slope value of m needs to be positive. This eliminates choices A and C, both of which show a negative slope for the equation with -3 as the y-intercept. Both remaining choices B and D show the correct positive negative slope values for the two lines, and so now we need to check the rise and run to identify the best answer. For choice B, the slope of 2/5, starting at the y-intercept -3, correctly goes upwards 2 steps and over 5 steps to cross at the point 5, -1. And the slope of -3/5 for the line crossing at -8 correctly goes down 3 steps and over 5 to cross at the point 5, -11, which proves this system of equations to be the best choice for this graph. Choice D doesn't work since the slopes are inverted for both equations. Another test question shows 2 equations, both in standard form, and asks for the solution. Since the star test version of Desmos cannot graph equations in standard form, you must first convert both equations to slope-intercept form, as shown here. Then graph them in Desmos to find the solution, -2, 3. This question asks for the x value of the solution point for these 2 equations. Again, to use Desmos to solve this, you must first convert the one equation in standard form into slope-intercept form. Then graph both equations to find the intersecting point and see the value of x to be 6.5, choice C. In the next lesson, you will learn how to solve this system algebraically using a process called substitution.